Okay, so welcome back to another video. So today's integral we have is over the positive reals from 0 to infinity of our integrand being ln of x divided by x squared plus 4 dx. So today's video is really not going to be that long. It's actually, I guess, relatively short video due to the fact that the way this is worked around is that it's just only going to rely on a couple of, some techniques specifically with u-substitutions. And another way, one of the steps we'll be utilizing is that we have to get a little creative such that we're actually using a u-substitution to the fact that we actually have to add a double quantity of what was given to the integral. So that sounds confusing to you. You'll actually see where I'm coming from with this. I actually covered this kind of, process several times from several, integrals back in the past. So once you see it, you kind of, familiarize with it eventually. So not too much, a lot going on. So that's just one of the big takeaways on how we're going to calculate this. So I think personally itself, I think the results of this is pretty interesting from all of this. So why don't you just jump right in? So let's start off by actually doing our little u-sub. Why don't we let u equals x divided by 2. And then if I want to solve for x by itself, that we have to plug it back into. So that means I have that x is equal to 2u. And so now differentiate both sides. So I have that dx is going to equal 2 du. So that's perfect. So I can actually substitute all this back into there. So now with that, let's actually now put everything back in together. So now our new integral is going to be from 0 to infinity. So nothing has changed since we're in the world of u. Now if I plug in for our dx differential, that's going to be 2, then du, and then now ln of, so x in this case is going to be 2u. Divided by, so x again, so that'll plug that back in, so I have 4u squared plus 4 and then du. So now with that being the case, I can actually factor out some constants over here. So factor out the 2 for 1, and I'll also factor out the 4, so I have a 2 over 4, so it means outside of that is reduced to just 1/2. Multiply with our integral from 0 to infinity of ln of 2u and then divided by u squared plus 1 and then du. Okay, so here's actually what we're going to do from this step here. Why don't we actually now apply some natural log properties to separate this out so we actually have ourselves in a form of a linearity of integrals. So of course I have a product inside of our natural log. We know that ln of 2u is the same thing as ln of 2 plus ln of u. So now separate this back together. So just write down 1/2, then the integral from 0 to infinity of ln of 2 plus ln of u, and then divided by u squared plus 1 and then du. So now rewrite this yet again. So I have, now that's a constant, ln of 2, so ln of 2 then divided by 2, the integral from 0 to infinity of, that's going to be 1 divided by u squared, which of course we know that that's a antiderivative we know how to calculate over here. And so now separate this, so that's going to be now 1/2 and then multiply the integral from 0 to infinity of, what is it, ln of u and then divided by u squared plus 1 du. Okay, so now this is our integral we're going to be calculating. So let me actually move to a separate marker, and then we're actually going to calculate this separate integral by itself. So now our integral we're calculating, so let me put a star asterisk over here, 1/2 the natural log of 0 to infinity of ln of u divided by u squared plus 1 and then du. So let's actually do yet another u sub. So why don't I actually call this u, we're going to let that set that be 1 divided by v. And so if I differentiate both sides, so that means du is going to equal to -1 divided by v squared and then dv. And then if I just plug all this back into over here, so now our new rewritten integral is going to be 1/2. And then before I do any sort of canceling out, why don't we actually put it out the way it is first. Plug into infinity, so this is actually going to approach 0. By plugging 0 over here, this is going to approach positive infinity. And so now I have the natural log of 1 divided by v. So under our denominator is, we plug this in, so what is it, u? So it's going to be 1 divided by v. I'll put that quantity square plus 1. And then we multiply with our du differential, so minus 1 divided by v squared and dv. Then what I do here is that we can actually now do some of this, manipulation / cancellation. So I have to switch the bounds, that's negative, and we already have a negative over here based on our differential substitution, so that's going to cancel. So let's see, 1/2, then the integral from 0 to infinity. So now that's going to be the natural log of 1 divided by v, and then divided by, so let's see, 1 divided by v squared, and then plus 1, I'll just multiply the v squared, so then that'll just become 1 plus v squared and then dv. And then another thing I can do here is that, yet again, applying natural log properties, I have a 1 divided by v as our, argument of the natural log. So that's the same thing as ln of 1 divided by ln of 1 minus ln of v, ln of 1 being 0. So now that's going to be a minus. So then this whole thing now becomes newly rewritten as -1/2 the integral from 0 to infinity of the natural log of v divided by v squared, or 1 plus v squared, then dv, whichever you want to write it, since it's the addition's commutative. Okay, so now that that's out of the way, so that's another way of rewriting the same thing as this thing over here. So let me actually denote this. So that's the same thing over here. So now what we're going to do here is that we're actually going to take the quantities such that we're actually going to add these two equations together. So let's say I call this thing equation number 1, this entire thing over here. And then the same thing, I just substitute this back, this is going to be equation number 2, substitute for the same thing. So let me actually make the distinction over here. So equation 1 is going to be rewritten as the same thing as, what is it? Let's see, ln of 2 divided by 2, the integral from 0 to infinity of, what was it? Yeah, 1 divided by u squared plus 1 du. And then it's a dummy variable, so I can actually just, replace this for the same thing. But first, let me write things one at a time. 1/2, 0 to infinity, and then what is it? The natural log of u divided by u squared plus 1 du. Okay, and then equation number 2 is going to be the same thing. So ln of 2 divided by 2, then the integral from 0 to infinity, so 1 divided by u squared plus 1 du, and then, as I mentioned, dummy variable, so -1/2 integral from 0 to infinity of ln of u divided by u squared plus 1, and then du. These two equations are the same thing. So then what I'm going to do is that I'm actually going to add up equations 1 and 2. And so this will yield us such that, first thing I should mention is that because of this, we can actually call this capital I. So that's the same thing as writing as 2 times I and then equal to. So we add these two equations together. So if I add these two, I'm going to have the natural log of 2 multiplied by the integral from 1 divided by u squared plus 1 du. And then now these two equations are actually going to cancel each other out. So plus or minus, that gets rid of itself. So that means the last thing is that all we have to do is that just calculate this antiderivative, which we know that its well-known antiderivative is going to be the arctangent of u. So ln of 2. And then next is, and then also have to divide the 2 by both sides just to get it by itself. So ln of 2 divided by 2, and then multiply by arctan of u. Evaluate this from infinity and into 0. And then what we have is that natural log of 2 divided by 2. We know that by plugging infinity, that's just going to give us pi divided by 2. If I plug in 0, then it means that's just going to give us 0. Then that means the final answer indeed is just going to be pi divided by 4 multiplied by ln of 2. And so with that, that is our final answer to this short integral that, well, I would call it short to the fact that the video is actually, short in itself. But, everything that I just explained is actually pretty simplistic and straightforward on how we actually, provide such the details to lead such an answer as that. So with that, there you have it. And yeah, that's pretty cool if you ask me.